Hi everyone, welcome to the first of 4 videos going through some past exam questions on equilibrium. So this first question here, we've been given our reaction. It's a reversible reaction, obviously. And it says, what does it say? In this reaction, 49 kilojoules of energy are released when 3 moles of hydrogen react. This is the enthalpy change of reaction. Okay. The temperature of the equilibrium mixture is increased. Describe and explain what happens to the position of equilibrium. So this is the idea of making changes to the conditions and seeing what effect that is going to have on the position of the equilibrium. So we need to use the idea of Le Chatelier's principle. Okay? And this is the idea that whatever change we make to the conditions, the position of equilibrium is going to shift to minimize the effect of that change. So if we've increased the temperature, the position of equilibrium is going to shift in order to decrease the temperature. So what we can say, so the equilibrium, this isn't the answer, but the equilibrium will shift. If we increase the temperature, the equilibrium is going to shift to decrease the temperature. So it's going to shift in the endothermic direction. Endothermic reactions are the ones that reduce the temperature, right? They absorb heat energy and cause the temperature to go down. So now all we need to do is go, right, which is the endothermic direction? Well, it says, what does it say here? In this reaction, so when they say this reaction, they mean forwards. 49 kilojoules of energy are released. So that means it's exothermic. So forwards is exothermic. So if the equilibrium is going to shift in the endothermic direction, it's going to shift backwards. So it's going to shift to the left. Okay. So what happens to the position of equilibrium? The position of equilibrium shifts to the left. So that's going to get us 1 mark and then the explanation for the second mark. And then, although it's a bit unusual in this case, the normal sort of standard way of answering this type of question is just to say something about the forwards reaction. And that's usually the best way of doing it. That's usually what it says on the mark scheme. So in this case, the reason it's shifted to the left is because the forwards reaction is exothermic. And so in this case, it's going to shift in the endothermic direction. And that's actually all we need to say. Position of equilibrium shifts to the left because the forwards reaction is exothermic. And that is sufficient. You don't need to say, oh, and the equilibrium is going to try and minimize the effect of the change, so it's going to shift in the endothermic direction because that's the way that's going to reduce the temperature. You don't need to go into all that detail. That is perfectly fine to get you the 2 marks. Okay. It's one of the few questions where the examiner will, take an implication from what you've written and accept that rather than you having to actually write everything out. So it's quite a nice one. We can be relatively short with it and just move on. Part F then says the total pressure of the equilibrium is decreased. So if we decrease the pressure, again, we're going to use this idea of Le Chatelier's principle, the equilibrium would shift to minimize that change. So it would shift to increase the pressure. To increase the pressure, you have more molecules of gas. So the equilibrium will shift to more gas moles. Basically, whichever side has got more moles of gas. So which side is that? Let's have a look. We've got 3 moles of H2 and 1 mole of CO2. So we've got in total 4 moles of gas here. And then on this side, I've got 1 mole of methanol and 1 mole of water. So I've just got 2 moles of gas here. So then in this case, it's going to shift to the side with more gas moles. So it's going to shift to the left again. Okay. So what's going to happen to the position of equilibrium? We're going to write this the same. The position of equilibrium will shift to the left. And then like we did with the first one, we're going to say something about the forwards reaction. So the reason for this is because the forwards reaction produces fewer molecules of gas. Okay. So if you can always get in that habit, you usually get the marks by saying the position of equilibrium is going to shift this way because of this is what's going on with the forwards reaction. And you could use moles or you could use molecules here. That would be fine. And you could say the right-hand side has fewer moles of gas. That would be acceptable. I just wanted to try and use the same wording both times just to make it consistent. But that would also be fine as well. Okay, so that was a bit of equilibrium shifting business. This question here says, what's going on? We've got another reaction here. Mixes some stuff together. Student analyzes the equilibrium mixture. Okay, they could potentially ask us about doing a calculation here, and they've got numbers, but that's not what they're asking in this question. They just want us to write the expression for Kc, for the equilibrium constant. Okay, and this is really easy once you know how to do it. Okay, it's always the same way around. So the equilibrium constant is always products over reactants. So we're going to have CO2 and N2 on the top, and we're going to have the CO and the NO on the bottom. Okay, the C in Kc stands for concentration. Okay, and so we represent the concentrations of these molecules by using square brackets. Okay, so to say the concentration of CO2, you put that in square brackets, and concentration of N2. And so then we're going to have concentration of CO and concentration of NO on the bottom. Okay. And then you'd multiply these together. You don't need to put multiplication signs in. You can do, but you don't have to. Then the other important thing is that each of these concentrations is raised to the power of the number of moles in the equation. So the CO should be to the power of 2. The NO should be to the power of 2. CO2 should be to the power of 2. And the N2 should just be to the power of 1. So that's fine. Okay. Then what are the units of this equilibrium constant? This is a bit awkward, but to work out the units, you substitute in the units. It's a bit of a strange concept, but concentration is measured in units of moles per decimeter cubed, right? So that's moles per decimeter cubed squared times by moles per decimeter cubed. And this is moles per decimeter cubed squared times by moles per decimeter cubed squared. Okay. So I'm going to then just go and work this out. So overall I've got moles per decimeter cubed to the power of 3 divided by moles per decimeter cubed to the power of 4. You happy with that? We'll just combine the powers there. 2 and 1 is 3, 2 and 2 is 4. So then if I do moles per decimeter cubed to the power of 3 divided by to the power of 4, and remember if we're dividing by, this is where you have to now have a bit of math knowledge. If we're dividing powers, you take them away. So it'll be 3 take away 4. So that's going to give us moles per decimeter cubed to the power of minus 1. Yeah, 3 take away 4 is minus 1. And now we just work this power into the bracket. So that's going to give us moles to the power of minus 1, multiplying 1 by minus 1. And then minus 3 times minus 1 is positive 3. So it's moles to the power of minus 1 decimeters cubed. And then we'd normally write that with the positive power first. If you write it that way around, you can actually say it out loud. So it would be decimeters cubed per mole would be the units in this case. And hopefully you can see how, depending on what the expression for Kc is, we're going to end up with different units every time. Okay, those are not just the units of Kc, they're the units of Kc in this reaction. In other reactions, Kc has totally different units. Sometimes it has no units, the units all cancel out. You can see if that was squared as well, then you'd end up with no units at all. Everything would cancel out. So you are going to have to work this out every time. You can't just learn what the units of Kc are going to be. Okay, let's do a couple more questions. Here we've got a quick one just about reaction rate, first of all. We've got this reaction, I'm pretty sure. Yeah, look at this, guys, right? Again, I'm sure I've spoken to you about this before, about exam boards being lazy. This is the same reaction that we just looked at, right? Hydrogen and CO2 making methanol and H2O. It's the same reaction, right? It's a completely separate question. Look, that's a question 3. And that's a question 4, so it's from a different exam paper, and they've just reused the same equation. Okay, look, it's minus 49 kilojoules per mole. This one we're saying releases 49 kilojoules of energy. So they're so lazy. This is why it's worth practicing these questions, because the same ones come up. Right, describe and explain the effect, a different question obviously, but same reaction. And describe and explain the effect of increasing the pressure on the reaction rate, not equilibrium. Read the question, right? This is not just the same question as this, where we was talking about changing the pressure, what's going to happen to the position of equilibrium. Changing the pressure, what's going to happen to the reaction rate. I see this all too often. People go, oh, reversible reaction, equilibrium, yeah, I know what I'm doing there. Read the question. If we're increasing the pressure, what effect does it have on the rate? So increasing the pressure increases the rate of reaction. Because if we've increased the pressure, there are more particles in the same volume. Because there are more particles per unit volume. And then if it's anything about rate of reaction, we want to be talking about frequency of collisions, right? More particles per unit volume, so the frequency of collisions increases. Okay, then it just wants us to write out Le Chatelier's principle. We've been using this all the way through. They don't really get very picky about the wording here. As long as you've got the gist of what the idea is, then they give you the mark. It's only a 1 mark question here. So there's no sort of specific wording you have to get exactly right for this one, as long as you've written pretty much the right thing. So Le Chatelier's principle, it's the idea that the position of equilibrium will shift to minimize the effect of any changes to the conditions of changes to the reaction conditions. As I said, you can word that in a lot of different ways, but as long as you've got this idea of, you can say counteracting the change, or there's a whole bunch of different adjectives that mean the same thing as that. Is that the right word? Adjectives? I don't know. My English is not as good as my chemistry. But yeah, you can choose a bunch of different words to go in there in place of minimize. As long as it means the same thing, you're fine. Right, then it says high pressure and low temperature would give a maximum equilibrium yield. Explain this statement in terms of Le Chatelier's principle. Okay, so now we're just going to talk about the conditions again. This is similar to the previous question, right? So high pressure would shift the position of equilibrium which way? Let's have a look. If we increase the pressure, the equilibrium will shift to minimize that change, so it would shift to reduce the pressure. To get a lower pressure, we're going to go to the side with fewer molecules of gas. So here we've got 4 molecules on this side and 2 on that side. So the high pressure would shift the position of equilibrium to the right, because, and then I'm going to copy what we've said here, right, on this question. The forwards reaction produces fewer moles of gas, because it's the same reaction, remember. So we're going to write that again. It was good enough for a mark last time, so it'll be good enough this time. And then the temperature, low temperature, just bullet point that just so it's clear. We're now talking about temperature. Low temperature would shift the position of equilibrium right, so if we lowered the temperature, it would shift the position of equilibrium, it would shift to try and increase the temperature again, because it's counteracting or it's minimizing the change. So it would shift in the exothermic direction, because that would cause the temperature to go up again. Exothermic reactions make things hotter, don't they? And we can see that the forwards reaction, they've given us delta H, this is always for the forwards reaction, so left to right. Delta H is minus 49. Minus 49 means it's exothermic. So that means it's exo forwards. We would be shifting it in the exothermic direction, we said, didn't we? So it would shift the position of equilibrium to the right. Does this make sense what we said? They're saying this would give the maximum yield of methanol. So both these things would shift the equilibrium to the right and give us more methanol. Okay, because we've got our methanol here as the product. So this makes sense, okay, with what we're saying here. Shift the position of equilibrium to the right because the forwards reaction is exothermic. Okay, and then finally, this is a bit of a different question. Explain why the actual conditions used by the chemical industry might be different. So we've just said this is what you should do to maximize the yield of methanol. They don't necessarily do that because there's problems with both these things. Okay, problem with using a high pressure is it's going to be expensive. It's going to take a lot of energy to generate that pressure, and it's potentially a safety risk. Right, the more you pressurize things, the more likely they are to burst, which could potentially be a problem. So we can say using a high pressure is expensive and a potential safety hazard. And using a low temperature was the other thing that we said should be the right thing to do. Problem with using a low temperature is you're going to lower the rate of reaction. It's going to make it slow. Because the particles don't have enough energy, the frequency of collisions is going to go down. We don't need to get into all that detail here because it's only 2 marks. So that's why we might not actually want to do those conditions. Okay, and so you'd come to a compromise. You'd find pressure somewhere in the middle, or temperature somewhere in the middle, and sort of try and get the best of both worlds.